Buyurun hocam, söz sizde.
Okay, so Soner, thank you for the invitation, and Tore, thank you for reminding me that I have a talk today. Otherwise, I think I almost forgot about it. Basically, I'm going to talk about a paper that we wrote with Emel recently. Emel Altaş is in Karamanoğlu Mehmet Bey University. And this paper was written to honor Professor Tekin Dereli's birthday. As all of you know, he has been a very influential person in Turkish gravity research, not only gravity, high energy research. So I would like to honor actually his work. Okay, so it will be basics, but even the basics are a little bit complicated. So please go ahead and ask questions if you like. And I have too many slides, but it doesn't matter. We can stop anytime you like. Okay, so let's see. How do we go down? Okay, so what are we going to do? First, the motivation of why studying this apparent horizon issue. And then I'll talk about the derivation of the apparent horizon equation. Plus, I will give a brief introduction to space-time split of the covariant space-time. And then after doing that, I'll write the apparent horizon equation in ADM coordinates. And then how you detect apparent horizon for a particular solution. And I will describe initial data for a black hole with momentum and spin, and I will actually conclude. Okay, so basically, by the way, you can read the paper. You will get a lot more information by reading our paper. Okay, so this is just a basic introduction. I will skip a lot of details of the paper. Since the first observation of black hole merger, I think it was in 2015, there have been many observations of merger of compact objects. And these observations have been with gravitational waves and other techniques, actually, when one of the collapsing object is a neutron star, or two of them are neutron stars. Okay, so essentially the gravitational waves, the profile of the wave, the amplitude and the change in the frequency produced by these mergers are consistent with the numerical solutions of general relativity. This seems like a simple statement, but it is actually rather remarkable. Okay, so whatever we observe, in fact, well, it is almost a tautology, because we can explain our observation by looking at the general relativity equations. By the way, let me see. Soner, benim yüzüm bir yerde çıkıyor mu?
Çıkıyor hocam, görüyoruz videonuzu.
Tamam.
Karşıda.
Tamam. Okay. So what I'm going to do is, first of all, I will talk a little bit about what is a black hole for a smart person that lives only for a finite amount of time. Okay, like you. So, and then I will describe an approximate analytical description of a self-gravitating system that has a total conserved energy, total spin, and linear momentum in an asymptotically flat space-time. So what we expect is this initial configuration of pure space, albeit randomly curved, not randomly, but non-uniformly curved. We expect it to evolve and settle into a single rotating black hole after emitting some gravitational radiation. So you understand?
Final configuration.
So this initial configuration that I will discuss at the end will settle into a black hole and emit some gravitational radiation. So I will describe the initial data, but from the initial data, I will show you that there is some, there could be some non-trivial gravitational radiation. So what is a black hole for a transient observer like us? We live for a short amount of time and die, right? So we have to be careful when we say there is a black hole out there. For stationary, which means Kerr and static Schwarzschild black hole solutions, they have rather dull lives. Stationary ones, just rotating ones, just rotate, do the same thing, and static ones, as observed by an observer outside the black hole, do nothing. So these vacuum solutions obtained in an isolated universe serve as our starting point for more physical and detailed understanding of actual astrophysical black holes. But actual astrophysical black holes out there in the sky do a lot of things. They have accretion disks, they have companion stars, they have like neutron stars, white dwarfs, black holes, whatever you have, they are feeding on these, right? So black holes are feeding on their environment and they grow. And in fact, if you think about it, they are the most dynamical parts of the vacuum. There is nothing there, but the vacuum still is dynamical. And the first LIGO and Virgo gravitational wave detection showed that black holes can grow feeding on other black holes. So two black holes can eat each other, become a larger one. That larger one can eat another black hole and then become even a larger one. So they are basically cannibalistic objects. And using this cannibalistic nature, we can perhaps explain the existence of intermediate mass black holes, which cannot be obtained from the collapse of a star. Okay? So since the astrophysical black holes evolved, concepts such as the event horizon, which are easily defined for eternal black holes, static and stationary ones, are not clearly adequate for us, right? You understand that the static and stationary ones do nothing, so they cannot explain the dynamical black holes. So what is the event horizon? Let's remember what that is. So event horizon is a codimension one null hypersurface in the totality of space-time, defined as the boundary of the black hole region from which time-like or light-like geodesics cannot reach future null infinity. The important thing is, in time, you have to go to infinite future to be able to say that there is a black hole inside the space-time. So a black hole, in principle, an event horizon is a global property of space-time. That means event horizon is non-local in time. You have to know the totality of all the events in the space-time, which we don't know, right? So basically, that definition of event horizon is no good for any practical purposes, right? You cannot locate it with experiments, basically. Okay, so I should say that the Event Horizon Telescope, the name, the Event Horizon Telescope, detected the environment of the black hole from which one can see at best the cross-section of the event horizon, not the event horizon itself. You can never know that there is an event horizon. You can only say that at best you have the cross-section, two-dimensional cross-section of a possible future event horizon. Sometimes event horizon is called the future horizon, okay? So for dynamical black holes out there in the sky, one needs to invent a more useful concept than the event horizon, which is the apparent horizon, which is now a codimension two spatial surface. Instead of a null three-dimensional surface, you have a two spatial surface, which means it is local in time. But since it is local in time and it's a two-dimensional surface, it unfortunately does not carry geometric invariant data as the event horizon. So you might say, Dan, this is coordinate dependent. Yes, it is coordinate dependent. So you have to be very careful about it. But what is good about this apparent horizon is that it contains sufficient information regarding the possible formation of a future event horizon. So there are theorems. I won't prove these theorems, but at the end I will tell you well, maybe I won't, but it just says that if the dominant energy condition is satisfied within general relativity, whenever there is an apparent horizon, there will always be an event horizon in the future. Okay? Now, in numerical relativity computations, detection of a black hole region in numerical relativity computations, detection of a black hole region is best done with the apparent horizon. And I told you within the context of general relativity, the existence of an apparent horizon implies the appearance of a future event horizon. Now, what you do in numerical relativity computations is that you excise the region outside the apparent horizon. That also includes the singularity for the stability of the computation, since nothing will come out of that region in classical physics anyway. So you cut that region out of your computation, and you do essentially, you work without singularities, okay? In modified gravity theories, apparent horizon need not be inside the event horizon. That is also important. Now, the apparent horizon. Sorry for that long introduction, but I had to do that. So as I just told you, the event horizon of a black hole as a null hypersurface cannot be determined locally. So one has to know the total space-time to define it. And the apparent horizon can be defined locally. And for that purpose, we need to define a congruence of null geodesics and its expansion. Basically, when I say null geodesics, think about light moving in space, okay?
Can I ask a question?
Yes, please. Who's that?
My name is Berk.
Yeah, Berk.
It is written that one has to know the total space-time to define it. I am not sure I understand the total space-time concept fully. Can you elaborate further, please?
So the space-time, the four-dimensional space-time is a collection of events, basically. And there is a causality structure on it. There is metric, there is causality structure on it. You have to know all the past and future of the, so let's not say past and future. You have a four-dimensional set on which the points are called events. You should know all the events to be able to say that there is a black hole in this space-time, okay?
So because of the singularity, we don't know it, I guess, because we don't know all the space-time.
No. Singularity is a different story because of the event horizon, actually. It is like this. Look, it will take my time, but let me try to explain this.
The global structure.
You need to know the global structure. Berk, it will take my time, but let me just explain it in 1 second.
If it's take too long, you can explain later.
Okay, so it will take, let's say, 1 minute for you, okay? So suppose I am here and I want to detect a black hole, whether there is a black hole out there, okay? And I want to throw a rock and then wait for it, right? Whether it will return or not. So how long should I wait?
Infinite.
Yeah, okay, so infinite, right? That's it, basically. Okay, so now let me define you.
Thank you.
Let's define well, I didn't say everything there, but later if you ask me this question, I can explain it more, okay?
Okay,
so,
thank you.
Because benden daha yakın birisi olabilir oraya. Ben attıktan sonra o taşı atar mı atmaz mı onun düşüncelerine de bağlı. Yani çok karışık olay. Okay, so you have to know the global structure of this four-dimensional space-time. So let's try to explain to you what the apparent horizon is, okay? We have an n-dimensional space-time manifold M with co-dimension one space-like hypersurface. So I already assume that the space-time can be defined as a product of time and space, okay? So if that's not the case, then you have a problem already, but that's not our concern, okay? So this sigma, sigma is n-1 dimensional, and we introduced a co-dimension 2 subspace S, whose dimension is n-2. And let n mu be a time-like unit vector orthogonal to sigma, and time-like unit vector, so its normalization is given as this guy, and S mu be a space-like unit vector orthogonal to S, so it is normalized like that. So here is the picture. Sigma is the spatial hypersurface, and the time direction is going in that direction, so this is n mu, and we choose n mu and S mu in such a way that they are orthogonal to each other. Of course, this S is, so let's stick to 4 dimensions. This sigma is 3-dimensional space-like, S is 2-dimensional space-like. Sigma is not the event horizon, as you understand. It is a 3-dimensional space-like hypersurface. I'm not using the event horizon here, okay? Now, instead of n mu and S mu, I could use K mu and L mu, which I will use, okay? So instead of these two vectors, and mu and s mu, I use k mu and l mu. These are null vectors, and there's a nice picture here, k mu, l mu, and l mu is outgoing null, k mu is ingoing null. So if you are not familiar with these things, you can imagine light propagating into the origin of S, defined by k mu, light propagating outward in the direction of L mu. Okay, so these are null vectors. Now, the induced metric on the hypersurface sigma is something called the pullback of the four-dimensional metric. You can write it like this, and you can check that this really is a metric on sigma, even though mu nu indices are four-dimensional. I will do everything in the n-dimensional setting because it is a lot easier. But this really, if you take a vector and try to project it using this vector in the time-like direction, orthogonal to hypersurface sigma, this vector evaluated on this metric evaluated on the vector will give you 0. So the induced metric on the subspace is similar. Basically, you have this equation 6, g mu nu plus n mu minus n mu. Now the important thing here is the following. Whenever you dissect the space-time into space and time like this, you are always going to need some kind of, you are defining time, right? That means you are splitting the metric into basically its components projected onto the plane and off to the plane. And that requires further knowledge of the hypersurface that you have. The hypersurface is embedded in the extra-dimensional manifold M space-time, and k mu nu is called the extrinsic curvature of this hypersurface. This is basically essentially the momentum of the metric gamma mu nu of sigma. Basically, it is the momentum, okay? Now here, so let me explain this. Here, this covariant derivative is metric compatible with the space-time metric. Now, if you are more interested in the geometric context, you can actually do it like that, but don't worry about it. I won't explain that. Equation 6 follows. So the extrinsic curvature, k mu nu, which is a spatial tensor living on the surface, is essentially the covariant derivative of the time-like vector minus this part, and this part can be written as acceleration if you like. So similarly, the extrinsic curvature of the n-2 dimensional subspace S is defined via the same procedure by equation 9. So we are going to need these. Now, if you use the induced metric and so on in a simple computation, you can get equation 10. Now, here is the basic definition. The expansion of the outgoing null geodesic congruence is essentially the divergence of L mu with respect to mu, but that is projected to on S with this induced metric Q mu. So this is the expansion of the null geodesic. So physically, it means you send light rays. What do? Do they expand or do they converge? Okay. Now, this divergence, basically, of the null geodesic congruence along its propagation, this is essentially that, okay? Divergence of the null geodesic congruence. Now, using our earlier definition of extrinsic curvatures, we can express this expansion in terms of purely extrinsic curvatures. That's why I defined that. So forget about equation 12, 13, and 14. Go to equation 15. Essentially, that null geodesic congruence, divergence of null geodesic congruence is essentially given by 15, where ij are space-like indices, okay? Now, I need to define for you the notion of a trapped surface before I can define the notion of an apparent horizon. The expansion of this theta is employed to define the very important concept of the trapped surface. An outer trap surface on sigma is a closed, which is a compact without a boundary codimension 2 surface, such that for all outgoing null geodesic orthogonal to the surface, one has negative expansion. Essentially, it is a surface, a two-dimensional surface on sigma, for which this divergence is actually negative, which means the light rays are converging, okay, everywhere on the surface. Physically, you are trying to send light rays out, but they don't go out, they go in, okay? The subset of sigma that contains the trap surface is called the trap region, which is a codimension 1 surface. Of course, this is a codimension 1 surface because it is a region on sigma, it is part of sigma. Now, finally, the apparent horizon is the boundary of the trapped region, and obviously special surface because it is the boundary of a special surface, which we shall denote as that. So you consider all the trap surfaces. There is one outer one, which is the boundary of it. And if you go a little bit more, if you send light rays, they will go out, they won't go in, okay? So by definition, apparent horizon is a marginally trapped outer surface. It's called MOT and satisfies the apparent horizon equation. Remember, theta negative means it is a trapped surface. Theta positive is like a free surface, non-trapped surface. Theta equals 0 is a marginally trapped surface. That defines the apparent horizon. Now, from this, if you consider time symmetric initial data, which means the extrinsic curvature is 0, because I told you that extrinsic curvature is related to the metric, so the derivative of the metric is like momentum. If the momentum is 0, it is time symmetric, then K is 0, and you have an apparent horizon which becomes a minimal surface in sigma or even in space-time. Okay, so the apparent horizon becomes a minimal surface for time symmetric initial data. Now, starting with this equation 16, I will use the ADM split of a generic metric and then basically try to solve this equation for you for one of the simplest cases possible. Okay, so any space-time manifold, essentially without any assumption, is locally decomposable into the ADM form like this. So you define these local coordinates, and since it is a curved space-time, it always covers an open subset of the manifold, not the totality of the manifold. Now, once this is given, you can write the extrinsic curvature as minus gamma dot of the three-dimensional metric plus some derivative terms, okay? That's why I told you that the extrinsic curvature is essentially telling you what the momentum of the velocity or momentum of the three-dimensional space-like surface is. By the way, this is n-dimensional, but I'm talking about, just for the sake of language, three-dimensional, I will use three-dimensional. So this decomposition is well known. Under this decomposition, the nice, beautiful covariant Einstein's equations split into Hamiltonian and momentum constraints and an evolution equation. So this was, remember, a beautiful construction. Einstein's equations as defined in 19 is not clear whether they are good as a partial differential equation, right? We don't really know that you have a well-defined initial value problem or you have a well-defined Cauchy data. It turns out you do have a well-defined Cauchy data, which was shown in 1953 by Schocker-Brua, which essentially said that given any initial data, three-dimensional hypersurface plus the momentum of that surface, you can construct a four-dimensional manifold which satisfies Einstein's equations. So that's a beautiful theorem. And I haven't written down the evolution equation. These are constraints to be solved on the surface.
Sorry,
yes.
Can I ask a question?
Yes.
Is it minus to the sigma at the beginning of first equation in 20?
20?
First equation in 20, is it minus to sigma?
Minus R sigma, actually. So Soner minus to the sigma ne olacak ya? minus.
Ben de onu anlamadım zaten nasıl.
Ya işte latek kabiliyetimiz çok yüksek değil. Sigma, R'nin sigması anlamına diyoruz yani.
Ha tamam pardon. O toplam anlamınız. Tamam pardon.
Olsun.
Ben de minus power sandım da.
Sağ ol canım
Tamam,
sağ ol. Uyumadığını gösterdim güzel. Şimdi bak bu 19'da bir R var ya. Bu R ile karışmasın diye bu sigmayı koyduk ama bu sigmayı buraya koymak da bir dert yani. R'ye çok yanaştıramadık. Anladın mı?
Tamam anladım hocam.
Yani
Sağ ol.
şey sıkıntısı var.
Tamam.
Latek kabiliyetimiz kısıtlı. Okay. Now, if you have not understood anything up to now, it's okay. Equation 21 is good enough, okay? This is the equation of apparent horizon. So you need to solve this equation. Kij of the three-dimensional surface, S is a normal spatial vector to the apparent horizon. If you can solve this, that's nice. But if you are interested in a more physical understanding of this, this is beautiful actually. You have this two-dimensional surface on space-time. Now, if you drag it along L, you get this theta L, expansion of that. So you have this two-dimensional surface, you drag it along the null, outgoing null direction. And if it is 0, then it's called the apparent horizon, okay? Now, in section B of the appendix of our paper, we also show this theta L from the minimization of the area along the outgoing null direction. So equation 22 comes from the minimization of the area, not in terms of time, in terms of outgoing null direction, okay? If you do that variation, you are going to get equation 22. If you set it to 0, you will get the apparent horizon equation. Okay, let us stick to 1 plus 3 dimensions. Now, yes. Tabii. Emine, sen misin?
Evet hocam. After this Lie drag definition, can we say that this theta is a scalar field?
Yeah, very good. Theta is a scalar field, but if you are more interested, you can define a theta mu nu as a tensor field. So this is the trace of that tensor. In our paper, you can find a theta mu nu and Richard-Hurry equation actually regarding this theta mu nu. So this can be upgraded. This can be upgraded into a rank 2 tensor whose trace is this, okay? Which has a symmetric part, which has an antisymmetric part, and they have all meanings, okay? I'm not going to be able to discuss them, but that's a good question, okay?
One more question, please.
Okay.
Can we set this theta inside any Lagrangian or something if it has a field kind of meaning?
Of course. Why not? If you are interested in that, you can do that. But what do you want to do with that?
Well, I don't know.
Okay, I mean, you can do it. But what I was trying to say is that variation of the area of S, any S, two-dimensional subspace along the direction of L already gives you equation 22, variation. Okay?
Yeah, okay.
Yani zamana göre minimizasyon değil de L yönünde minimizasyon veya optimizasyon, ekstremizasyon yaparsanız bu çıkıyor. Bu aynı zamanda theta mu nu isimli bir tensörün trace partı, simetrik olmayan bir tensörün trace partı. Çok önemli bir nesne. Richard-Hurry bunları kullanarak bir parça singularity teoremlerini yakaladı. Ardından Penrose onları kullandı. Okay. Rica ederim. So, assume now that the local coordinates on sigma are denoted as r theta phi, just regular r theta phi coordinates, okay? Now, basically, the location of the apparent horizon depends on theta and phi. So we can actually think of r as a function of theta and phi because r theta phi defines sigma, and if you give r in terms of theta and phi, it defines a two-dimensional space. Now, if you write down the equation carefully, that apparent horizon equation, you get this. Okay, so what kind of a surface are we going to describe? Typically, we are talking about nice surfaces, which are smooth, you know, it doesn't have cusps or anything like that. So we are going to describe it as a parametrized level set. If you are interested in other types of apparent horizons, where there are cusps and some other maybe discontinuous and so on, you need to generalize this, but let's do it for the simplest case, okay? So phi equals 0 gives you, the level set of phi gives you the location of the apparent horizon, h being a sufficiently differentiable function, essentially, okay? Since SI is normal to the surface, basically one has SI as the gradient of phi, and because it's a normal vector, we put a lambda in front of it, and we define m to be just the gradient, which essentially yields SI is in the form of 25. Now, at this stage, we have to do some simplifying assumptions. Otherwise, things get really complicated. So to proceed further, let us consider the metric on sigma to be conformally flat, which was assumed by Bow and York long time ago. It actually is a very physical thing to do, but sometimes you need to generalize this assumption. Okay, let me not say in which cases you need to generalize this, but this is not the most generic one, as you can understand, but let's assume that the metric on sigma is conformally flat. Okay, then under these conditions, SI and lambda can be found. Long calculations, sorry, you have to check them in the paper. So after working out each piece carefully, the location of the apparent horizon, that means finding h, is given by this highly nonlinear exact partial differential equation, okay? So given the metric and the extrinsic curvature, this guy is gonna tell you where the apparent horizon is or whether there is an apparent horizon or not. So for numerical relativity people, this is the equation to be solved. If you are saying that there is a black hole, this is what you mean. This has a non-trivial solution, okay? So equation 29 under the assumptions of conformally flat initial data. Now, our goal here in this paper, well, not in this, in the paper that I have given to you, well, actually, there is another paper that we wrote. So in the paper that we wrote with ML, I think this year, is basically give an approximate analytical solution to some physically reasonable initial data, which must satisfy the Hamiltonian and the momentum constraints on the hypersurface, which we discuss next. So initial data for a single black hole with momentum and spin. When I say single black hole, you shouldn't think of it as a Kerr black hole or Schwarzschild black hole. What I mean is, in this sense, there is some curvature there, highly terrible curvature, and it has an apparent horizon, okay? That's what I'm trying to say. If you wait long enough, it could settle down to one of the black holes that you know. So since we are talking about a vacuum, T min is 0, and the sigma is the Cauchy surface, Kij is the extrinsic curvature as defined before, and D is the metric compatible connection, and the metric is the three-dimensional metric. So I'm going to now work with three-dimensional objects, okay? So again, assume conformally flat space, phi positive or negative, it doesn't matter, but you need to choose the sign of phi. You cannot have a change in phi, and assume furthermore, you have a maximally embedded hypersurface. So this trace of K, the extrinsic curvature vanishes. If you don't assume this, things become a little bit more complicated, but you can assume that this is 0 to search for reasonable analytical data, okay? Now, under these assumptions, and the Hamiltonian constraint reduces to an elliptic equation, a nonlinear elliptic equation, and the momentum constraints reduces to a linear equation. So you really have a beautiful equation in 35, which you can solve exactly, and then go back and put it into equation 34 to solve this elliptic equation. Now, this d hat here is compatible with the flat metric of the conformally flat three-dimensional hypersurface. Now, the momentum constraint, you can solve it, can be solved easily. And there are many solutions, but we choose here a 6-parameter solution. So this is the solution that we choose. If you take it, plug it in here, it is a solution to equation 35, except not at r equals 0. Forget about r equals 0. That'll come later. Now, we are going to assume the asymptotic space to be conformally flat. That basically means limit of this phi conformal factor as r going to infinity is 1 plus e over r. If you have studied the Schwarzschild metric in the conformally flat coordinates, you must recognize why I have chosen equation 37. Or if you know the ADM energy, you might recognize that ADM energy, this ADM energy for an asymptotically flat surface is a geometric invariant of the three-dimensional surface computed on the two-dimensional sphere at infinity. And if you plug in the metric that we have, it just reduces to the derivative of phi. Now, there is r square here. So if phi goes like 1 over r, you are going to pick up a 1 over r square. So to get a finite energy configuration, you need phi to go like e over r. Okay, that is the idea. Now, if you compute Kij to solve the elliptic equation, you get this non-trivial actually looking object. Now, without loss of, by the way, I didn't explain to you here, but if you compute the ADM momentum, you get P to be the ADM momentum. If you compute the spin of this object vacuum, the spin becomes J. So it is a spinning finite energy object which has a linear momentum. So the vacuum is moving in some direction, it is rotating and it has finite energy. All these things are computed at infinity. That's why they are all conserved, okay? Now, without loss of generality, let us choose our coordinates to be in such a way that the spin is looking in the K direction. And again, without loss of generality, choose the momentum of this object to be like this with some theta 0 to be a fixed angle. Okay. Then you come, let's define these two constants and you are supposed to solve equation 44. So it's a nonlinear elliptic equation and you need to solve this. By the way, you can really show that it has a solution and its solution is unique, basically. Well, if it has a solution, its solution is unique. That's easy to show, okay? But since it is nonlinear, highly nonlinear, it's very hard to solve this and nobody has been able to achieve a solution in the exact form. So let us, by the way, of course, when the momentum is 0 and the spin is 0, you can solve it. That would be the Schwarzschild solution, okay? Initial data for the Schwarzschild metric will follow when the right-hand side is 0. When the linear momentum and the spin comes into picture, the problem gets highly more complicated. Okay, so let us try to solve this in a perturbative manner, meaning that it is a slowly moving, slowly rotating object, and then we do a perturbation. Sonra 4.30'da bitiyor değil mi?
Hocam 4.30'da bitiyor ama dediğin gibi sonrasında bir şey yok. Zaten free discussion. Rahatınıza bakın.
Tamam. Şimdi denklem çok nonlinear olduğu için çözemiyoruz. Numeric computation gerekiyor ama analitik olarak ne kadar ilerleyebiliriz sorusunu sorarsak şu denkleme biraz bakmanız gerekiyor. P'yi çözeceksiniz. Burada P kare var. So you have P square here. You have JP here. You have J square here. And these are assumed to be small. Small what? With respect to what? With respect to energy, okay? Small with respect to energy. Then, basically, you make an ansatz like this. There is a phi 0, there is J square, there is P square, there is JP. you don't have odd terms, of course, then you do a regular perturbation theory. It is lengthy, so let me not go into the details, but you can solve this. At the lowest order, you have this 46. At order 0, you have this phi 0, which is just the Schwarzschild type solution, 1 plus A over R. If it is exact Schwarzschild, this becomes M over 2 or something like that, right? M over 2, A becomes M over 2. Now, at the second order, you have this linear equation, this linear equation, this linear equation. Now, to solve these linear equations, you resort to the spherical harmonics, because here you have the Laplacian, but this Laplacian is in three-dimensional space, and you look at the right-hand side to pick up the correct spherical harmonics. So we search for spherical harmonics, and then at the end of the day, basically, you can find the solution at this order for phi j to be given like this, where phi j is something like this. So it is complicated. You see, there is this part and there is this part. Now the JP part, if you work it out, it gives you 0 for the lowest order, but the first order or second order, it gives you 56. You are solving linear equations in perturbation theory. For phi p, now this is complicated. It reduces to 4 different equations, 1, 2, 3, 4. And if you look at the equations, they're similar, but the solution is actually a little bit complicated. So, but still you can solve it with some boundary conditions, okay? At the end of the day, you can collect all these parts. So what did I find? I found the conformal factor for a slowly moving, slowly rotating, finite energy initial data, which can be possibly interpreted as a black hole in the future. Since it is not nicely curved, it has some gravitational radiation in it, okay? So collecting these parts together and then expanding looking at order 1 over R, you get the conformal factor to be exactly like 61. And using the ADM energy computation, you find that the ADM energy, finite energy of this thing is essentially 2A plus J squared divided by this plus that. So it has some zero energy, it has some rotational energy, it has some kinetic energy. So yani aslında baştan size sorsaydım bu nesne nedir diye, kütlesi m olan j kare şeklinde bir dönme kinetik enerjisi olan 1 bölü 2 mv kare şeklinde ya da p kare bölü 2 m şeklinde olan bir şey var derdiniz. Ama sayılar tutmuyor dikkat ederseniz. Bu da teorinin nonlineerliğinden geliyor. Okay. Now here at this stage, we can define something called irreducible mass of this object. Irreducible mass concept is very important actually. In classical general relativity, black holes can merge, do all sorts of things, but there is some quantity which is not going to decrease. It can only increase, and eventually it will turn out to be related to entropy. And this irreducible mass is basically related to the square root of the event horizon divided by 16 pi. But since we don't have the event horizon, here we have the apparent horizon. So it is an assumption or an approximation, okay? So that 63 is that. Now, after all these, we still don't know where the location of the apparent horizon is. So we need to solve the apparent horizon equation as an approximate solution. So H0 plus PHP plus JHC. If you look at carefully, you realize that you do not need P square and J square and the rest. All you need is at order this, because essentially you are going to take the square of this thing to find the area. Now H0 has no, well, it's a constant, basically that's what I'm trying to say. Ignoring all the higher order terms, now we have this apparent horizon equation for this configuration that I noted. Now we still have this terrible equation to solve, okay? Now, it's always a better idea to go to I gave you the apparent horizon equation in Cartesian coordinates. So after a coordinate transformations, I gave you the Bow and York initial data, the solutions for K in Cartesian coordinates. So you need to go back to the, what do you call this, spherical coordinates. And in the spherical coordinates, equation 69 arises. So this is the equation to be solved to get the location of the apparent horizon. Okay, at the lowest order, we have this. And so phi is 1 plus A over R. So we get H0 to be A. So this explains the physical meaning of the integration parameter A. It is the location of the apparent horizon at the lowest order. Okay? At the next
wasn't A like, sorry, wasn't A like mass?
Mm-hmm.
So dimension-wise.
Very nice, very nice. The mass was something like this. Look, 62. The mass is like mc squared, this one, right? It's not exactly like mass, right? And not exactly like mass. This is not a relativistic Einstein dispersion relation. Yani şöyle değil mi? P kare, C kare artı M kare bilmem ne şeklinde değil ya bu denklem.
Yeah, no, my point was, what's the dimension of A?
Yeah,
like in SI units.
It's like mass. Of course.
Okay, so but you also showed length was like A. Shouldn't be like inverse. But
Sure.
shouldn't be like A to the minus 1.
Have the same dimensions, yeah?
Yeah, in the next equation where you showed that H0 was A, 71. Shouldn't be like A to the minus 1 dimension-wise. Like length is like inverse mass.
Hayır. Mass ile length aynı dimensionlarda. A bölü R bak. Mass and length have the same dimensions.
Pardon yani şey.
Yani ben neyi kullanıyorum? Geometric unitleri kullanıyorum. So I'm using geometric units.
Okay.
G is equal to 1, C is equal to 1, okay?
Okay, so I was thinking of something else. My bad.
So for the first time, now we are learning that H0, which is the lowest order approximation to the location of the apparent horizon is A, okay? Now at the next order, I have to solve equation 72. Look at, and 73. Look at this, it looks like a terrible equation. You see, this is that, and this is like a Laplacian on the sphere. This is a source term. This is the Laplacian on the sphere. And I have to solve the Laplacian on the sphere with a source, plus I have to solve the vacuum Laplacian on the sphere without any singularity. Okay, that's the important thing. I cannot accept any singularity. So next task is to find everywhere finite solutions of this equation. Laplacian on the sphere plus the Helmholtz equation, equation 74. Okay, so the Laplacian on the sphere is given as 75. Now, what do you do? It's best if you use Green's functions technique, and basically it's not difficult. You can find the Green's function for the Laplacian for the Helmholtz operator on the sphere, and it is this equation 77 is the Green's function in this closed bounded space where x is this and x prime is another point, and this is the symmetric Green's function. Now, employing this Green's function, I was rather amazed that you can actually exactly solve this equation, okay? And it turns out HP is minus 1 over 16. This one, HJ is 0. So we have determined the location of the apparent horizon for a massive rotating, moving object, equation 79. Now I have to tell you this. Before our computation, somebody did the computation for J equals 0 P non-zero. Somebody else did the computation for P equals 0, J not 0. So our computation covers both P and J non-zero. And actually it is quite non-trivial, okay? Now, if you want to plot this, here is this two-dimensional surface. There is a dimple here. You see, there is a dimple here. And then because the curvature is not uniformly distributed, it will essentially evolve into a black hole, hopefully at the end, and emit some gravitational radiation. Okay? But let's try to understand the area of the apparent horizon. Now, M is the metric on the apparent horizon, and this will be the usual definition of the area. And if you plug everything in it, 81 is exact. Now, if you take the conformal factor, if you take the location of H, by the way, looking at 81, you realize why I did not consider P square and J square in H. You see, H comes with H square. That's why I didn't actually consider them, okay? At the end, one finds the area of the apparent horizon to be given as 82. And the angle between the spin and linear momentum does not appear in the area. By the way, the location of the dimple depends on the angle between the spin and angular momentum of the apparent horizon. Now, from that, we can define the irreducible mass. Remember, irreducible mass is the square root of this divided by 16 pi. So irreducible mass, whatever this guy does, it cannot reduce this classically, is given by this 83. Comparing 83 with EADM, we get EADM of this object to be irreducible mass plus P squared divided by irreducible mass plus this. So what I like about this result is that in turn, this exactly matches Christodoulos, I think 1970 paper, where he defines the irreducible mass for the Kerr black hole, okay? So he's asking, in this paper, he's asking, what is, if you do something to a black hole, if you throw a rock or whatever, or if black holes merge, what can you not reduce? You cannot reduce to irreducible mass. And he shows that at the end of the day, the total ADM energy is given by some formula in which for small p and j, you get this, okay? So what we have done up to now, we have presented a step-by-step construction of the apparent horizon equation, which is extremely important in black hole physics. And essentially, we showed it, how it works for a slowly moving and spinning black hole. For stationary black holes, the event horizon and the apparent horizon exactly coincide. This is important. If the black hole doesn't do anything or it does the same thing, like rotate, event horizon and the apparent horizon coincide in nice coordinates. You shouldn't use terrible coordinates. Now, I have skipped some interesting issues. For example, you need to solve numerically the case for multi-black holes, two black holes. Actually, Emine here is working on two black holes. And here is the interesting thing. If you assume dominant energy condition, this is what I like. It's a beautiful theorem. The topology of the apparent horizon in general relativity is just S2. You cannot have any other topology, okay? There is a slight caveat there. T2 is also possible as a limiting case, but this is a beautiful theorem where you use the Gauss-Bonnet theorem in 2 dimensions to show essentially that Einstein's equations demand that the total scalar curvature on S is positive. Now, momentum constraints in general relativity are easily solved with the method of Bowen-York for multi-black holes. Belki çok kimse bilmiyordur bunu. İsterseniz 1 milyon tane kara delik olsun. You can solve the momentum constraints in general relativity, while the Hamiltonian constraint is always an elliptic equation, a terrible equation, which you have to resort to numerical computations. Okay, so here we extended the earlier work of Dennis and Baumgarten, who considered essentially approximate initial beta for non-zero P, and Gleiser and et al. For spinning black holes. Now, we computed the properties of the apparent horizon, such as its shape and the surface area, and showed that dependence of the shape on the angle between the spin and the linear momentum. So the space apparent horizon is curved depending on where the total spin and linear momentum are pointing. Remember, the spin and linear momentum do not change. It is the conserved spin and linear momentum of the totality of space-time. And we calculated the relation between the conserved quantities such as the ADM mass, the spin, the linear momentum, and the irreducible mass. The area of the apparent horizon does not depend on the angle between, does not depend on the angle between the spin and linear momentum. The area does not depend on the angle, but a dimple arises. And that's it actually. So I'm almost out of time. So thank you for listening.
Thank you so much for this beautiful talk. So does anyone have any questions?
Yes, I have one. May I ask it?
Please.
Thank you. Okay. Thank you for the lecture, Hocam. My question is related to, I think, related to small point actually. We have used the term conformally flat a lot back in the slide, yes. Actually, recently I came across the term in context of the Polyakov action, where we use the Weyl invariance of the action there to use this Weyl transformation and use this conformally flat thing in order to simplify the equations of motions which happen to be nonlinear. So my question is that it is the same thing that we use here to make a conformally flat thing, or if not, what it is and what enables us to do that?
Okay, Boran, thanks for the question. In 2 dimensions, you can always choose a conformally flat coordinate system. That is always possible. Okay, always possible. There is no problem with that. But in 4 dimensions, this is an assumption. Okay, I didn't tell you, but there are some cases which cannot be explained by this conformally flat choice. Okay, so this is a choice in 4 dimensions and in 3 dimensions, but in 2 dimensions, you can rigorously show that conformal flatness is just a choice. Okay.
I see. So here it is not a choice, but it is an assumption.
Exactly. It's a simplifying assumption.
Okay. Thank you very much.
You're welcome. Good question, by the way.
Thanks, Boran. Are there any other questions or comments?
Yes. Bayram, do you take or do you make an assumption about the topology of the apparent horizon in the beginning? As if you assume that the topology is spherical. That is, the earlier number is positive or negative. Can we have a toroidal apparent horizon? Or is there a limit? Is there a limit?
So here is the idea. What we have done here is everything is local and the topology does not enter into the picture, but here is what you can show rigorously, very rigorously, no problem with that, okay? If you take Einstein's general relativity and the dominant energy condition, basically you can prove that the integral of the scalar curvature integrated of the in the apparent horizon is, which is the Euler number, is actually positive. Okay, so that means the topology is S2, spherical. But is it positive or is it greater than or equal to 0? If it is equal to 0, you can have a toroidal topology. Yani toroidal topology de mümkün, but classical general relativity theorem is so people usually say, okay, you can show that it is actually.
So I am wondering whether in a special interesting limit can we go to such topology?
Exactly, you can go to such topology. In fact, when black holes merge, toroidal topology sometimes arises actually during this transition, and you have a toroidal topology. In fact.
Thank you.
Yeah.
Thank you. Any other questions or comments?
Sorry, if there isn't another question, may I extend my question a little further?
Yeah.
Related to this Weyl invariance thing. In that case, in that scenario, in the two-dimensional place and in the context of Polyakov action, this Weyl invariance result in a gauge freedom, right? So even if it is not a choice in here, but is an assumption, does this assumption result in a gauge freedom, or does this spoil anything about our solutions? I am not familiar with the subject very much, but actually, I am trying to understand the consequences of this assumption.
Actually, so let me say what I said before. It is an assumption, which means you can only capture certain configurations, right? You cannot capture all possible configurations. Now, recently, in the last 10 years or so, I think, it was shown that the Kerr black hole, rotating black hole, does not admit a conformally flat three-dimensional hypersurface. So you are really missing. For example, if you want to write down the Kerr black hole in a conformally flat coordinate system, you can't do it. That's basically the thing. Okay, so you are missing some of the interesting stuff when you do this computation.
Okay, thank you very much again, Hocam.
Yeah.
Let's thank our speaker again. Thank you so much, Hocam, for this beautiful talk.
Teşekkür ederim, ben çok sağ olun.